Hello and welcome to the third installment of the Learn Julia for Control lecture series. Today we'll talk about time responses, time response simulation, and the proper documentation page to learn about this is labeled time and frequency response. And we see we have doc strings for things like impulse, lsim, step, and so on. We also have some documentation for the plots here, the corresponding plots. All right, here I have VS Code loaded, and we're gonna start by loading the control system base package and the plotting package. And then I create a double mass model, so that's from our demo system library. It looks like this. It has 4 states, and in this case, 1 output. Here I just indicate that I want the velocity of the first mass as output. Initially, I will discretize this system using zero-order hole and a sample time of 1 millisecond before we simulate. I'm going to show you later how we simulate in continuous time. And generally, discrete time simulation is much faster. So that's why we start there. I have now discretized the model, and it looks like, it looks like this. I can call the function step, and then the second argument can be a variety of things. Here it's just the final time, and that gives me a result. We see it's called sim results. If I print res to the terminal, we see that it contains the system we simulated, time vector, and these arrays here that contain the result. But I can plot that result immediately. So I say plot res, and we see. We do a step, it wiggles a bit because it's this mass spring damper system, and then the static gain appears to be around 0.5. Similarly, I can call impulse also for 5 seconds, and here's the impulse response. I could also provide a vector here, so from 0 in steps of 0.1 until 5. It's a discrete time system, and this must match the sample time of the discrete time system then, so that would work. It's actually good I made that error so we could clarify that. We see it says time vector must match sample time for discrete system. And we can plot that. But this result object now, if we want to get the output, we can get that. What did I do? Using the field y. And we see it's a 1 by 5,000 matrix. So some other control system packages will give you a vector here, but or a matrix that is the transpose of this matrix. In Julia, you get it 1 by, so this would be the number of outputs, and this would be the number of time points. And the reason it's done that internally is for performance reasons, because that's how it's this order that Julia stores the memory. We can also access the states. The display is unfortunately a bit messed up. I'm not sure why. Let's see if I can make that look nicer. Yeah, okay. So here you see it's a 4 by 5,000 matrix in this case. So these are the different state components, and these are the time points. All right, let's zoom in again so we can see. And adjust here. All right. We can also get the time vector that is stored inside the result. And the system that was used to perform the simulation is also stored. If we don't want to keep this result structure, we can also immediately unpack these arrays. So if we call impulse with this syntax here now, we have y available already here. All right. So this was step response and impulse response simulation. Notice that these never plot anything, these functions. You have to call plot on this result, or you can of course plot these arrays manually. Just keep in mind that X is now this transposed matrix. If you want to plot it manually, you have to transpose it like that, and then you get the state trajectories. If you want them in separate plots, we say layout equal 4. or we can also be more specific and say 4, 1, and then we get a plot like that. All right. When we call the function lsim, we have the option to provide an input that is a sample, a vector of samples. However, if we use a vector, so this is now a vector, then lsim will complain and say that you must have size, gets a bit of a confusing error message here. We got size 100. And the problem here is that u has the wrong layout. We should use a matrix where we have the number of inputs times the number of time points. So if we say random 1, 100, we now have a 1, 100, 1 by 100 matrix instead. And that works to pass to lsim, and we can plot that. By default, we only get the plot of the output, but if I say plot u equal true, I get also the input, and we have a plot x also if we would like to see that. So here we have the output and the input. And since this is discrete time, by default it shows this kind of step version of a plot. Here I create a multiple input, multiple output system, and I once again call the double mass model function, and here I specify that I want all 4 outputs, and I want also an input for load disturbance. And I discretize that with a millisecond sample rate. The system looks like that. Now I create a matrix U here as input, and we see it has size 2 by 100. And the first row corresponding to the normal input of the system is just random numbers. But the second row is a step. So this is the vector 1 to 100 transposed, and then I broadcast this inequality operator. So the result of this would be a vector that is, we can plot it, and then I need to actually remove the transpose for the plot. We see it becomes a step function where the first 50 values are 0 and then the next 50 values are 1. I can call lsim with that, and now I get I say here plot u equal true, so I get the outputs. Unfortunately it's a bit cropped. That happens sometimes, that this plotting backend crops the labels here. And then we can say margin is 5 plots that millimeter. And now I get a bit more margin. Maybe I need a bit more. All right. So that's an option to control automatically if it screws up like this. All right, so here we have the 4 outputs, y1 to 4, and then the 2 inputs. Now, so far everything has been simulated in discrete time, and that is nice and fast. But we can also simulate in continuous time, and to do that we need to load this control systems package, and that takes a bit longer to load than to load the control systems base. So if you don't need it, you don't have to do that. I create a new double mass model. This time I do not discretize it, and now I can call step on this continuous time system. We see it prints here as a state space continuous. I get the result and I can plot that, and it looks the same, but it's no longer jagged like it was before when it was discrete time. So far we have seen how we can call lsim with an array u, so u has been like a matrix in this case. We can also use a function u as an input. So here I create a state space system. It's just a double integrator in discrete time. Create some cost matrices, Q and R for an LQR problem, and I compute the optimal feedback gain L. And then I create the function here, u. In this case I create an anonymous function. So this function takes x and t, and it computes negative L times x for negative feedback. And then it also does this thing here. So if time is greater than or equal to 2.5, this will have the value 1, otherwise it will have the value 0. And then we multiply by 1.5 here. So this adds kind of like a step disturbance of magnitude 1.5 occurring at t equals 2.5. So I can pass that function as an input to lsim. I can also provide the initial condition here, x0. And actually modern versions of Julia, you don't need to write x0 is x0. You can just write like that. But then it's important to, this semicolon is the separator between positional arguments and keyword arguments. If we write like this, it's obvious that this is a keyword argument because we're using keyword syntax. But if I just want to pass it based on the name here of the variable, I need to indicate that this is in fact a keyword argument. All right, so I can call lsim with that, and then I plot the results, and I say that I want to plot u as well. So we see the output, and here we see the input now, and at 2.5 we take a step. So that would be the disturbance I added here. If I had removed that, we would just see that it converges to 0, and the input also converges to 0. All right, so that was a brief overview of a time domain simulation. And underneath the hood here, when we call lsim, there is an ODE integrator that solves the problem. Not in this case, because this was a discrete time system. But in this case, here, in this case, there is a ODE integrator. If we look at, we need to look at the docstring for lsim. We see that, let me make this a bit bigger. We see that we can choose the algorithm that is used for simulation. So it's called method here. No, sorry, it's called, I'm confused. Actually, let me show you another way. So this control system toolbox is entirely implemented in Julia, which means that it's quite easy to go and look at the source code. So here I call the function step. If I say add edit in front of that step, now I will be taken to the part of the code that is actually called here. So it calls step with an LTI system, that calls step with a particular vector. And that calls this function, so this is step now with a vector t, and it gets this vector t from default time vector here if none is provided. And then inside here it calls lsim. All right, so we can go to the lsim method if we want, and I happen to know that we need to go somewhere here. Oh, let's get rid of the linter if we can. All right, so here we have the function lsim, the method that accepts a continuous time system and a function u. And that calls solve on an ODE problem, and it passes in an algorithm here. And that algorithm can be customized. And it defaults to the tsit5 algorithm. That is similar to ODE 4.5 Runge-Kutta style algorithm. But if we had a very nasty function here, or we had a very stiff system here, perhaps maybe we would like to use a different integrator, and that's possible to do that. You can customize the integrator that's used underneath the hood. And all the other keyword arguments that are passed into lsim, they are passed along to this solve function. So if you would like to customize some other aspect of the ODE solution, you can do that also. All right, and then in the end here, everything is packaged into a sim result. We can have a look at how the sim result looks. It's just a basic struct that contains the arrays and the system that we used. All right, the next topic will be, let's see here, it will be closed loop transfer functions. We will go into a bit more depth of how to create closed loop transfer functions. And yeah, until next time, thank you.